Welcome, class, to Applied Mathematical Concepts. So this is the first chapter that we are starting for this year, and it is called Problem Solving and Critical Thinking. Don't forget you can see the book online in Google Classroom. Anything that you miss in class, you can go back and look there if you need to see anything out of the book. So this first chapter is literally about how to solve some problems and using your brain to do it. And so we're going to go through this. If you look on page 1, it says problem solving, critical thinking. How would your lifestyle change if a gallon of gas cost $9.15? Or if the price of a staple such as milk was $15? That's how much these products would cost if their prices had increased at the same rate college tuition has increased since 1980. If these trends continue, what can we expect by the 2010s and beyond? We can answer this question by using estimation techniques that allow us to represent the data mathematically. With such representations called mathematical models, we can gain insights and predict what might occur in the future on a variety of issues ranging from college costs to global warming. One of the new frontiers of mathematics suggests that there is an underlying order in things that appear to be random, such as the hiss and crackle of background noises as you tune a radio, irregularities in the heartbeat, some of them severe enough to cause a heart attack, or irregularities in our sleeping patterns, such as insomnia, are examples of chaotic behavior. Chaos in the mathematical sense does not mean a complete lack of form of arrangement. In mathematics, chaos is used to describe something that appears to be random, but is not actually random. The pattern of chaos appears in images like the one shown on the left, called the Mandelbrot set. Magnified portions of this image yield repetition of the original structure as well as new and unexpected patterns. The Mandelbrot set transforms hidden structure of chaotic events into a source of wonder and inspiration. Many people associate mathematics with tedious computations, meaningless algebraic procedures, and intimidating sets of equations. The truth of the mathematics is the most powerful means we have of exploring our world and describing how it works. The word mathematics comes from the Greek word mathematikos, which means inclined to learn. To be mathematical literally means to be inquisitive, open-minded, and interested in a lifetime of pursuing knowledge. Mathematics in your career, generally speaking, the income of an occupation is related to the amount of education required. This, in turn, is usually related to the skill level required in language and mathematics. With our increasing reliance on technology, the more mathematics you know, the more career choices you will have. Mathematics is a science that helps us recognize, classify, and explore the hidden patterns of our universe, focusing on areas as different as planetary motion, animal markings, shapes of viruses, aerodynamics of figure skaters, and the very origin of the universe. Mathematics is the most powerful tool available for revealing the underlying structure of our world. Within the last 30 years, mathematicians have even found order in chaotic events such as the uncontrolled storm of noise in the nerve cells of the brain during an epileptic seizure. Mathematics involves the study of patterns in everyday life. We frequently rely on patterns and routines to draw conclusions. So here in the book is an example on page 3. It says, the last 6 times I went to the beach, the traffic was light on Wednesdays and heavy on Sundays. My conclusion is that weekdays are lighter traffic than weekends. So this is what we call inductive reasoning. Whoever this person was went to the beach 6 times or 6 weeks in a row, and on Wednesdays it was light traffic, on Saturdays or Sundays, I guess, it was heavy traffic. And so that was a pattern that this person followed. And so they made what we would call a general conclusion based on those specific days of the week that they went. So that is inductive reasoning. So this is your first question there on your notes. Inductive reasoning, the study of patterns and routines, and the process of arriving at a general conclusion based on observations of specific examples. Although inductive reasoning is a powerful method of drawing conclusions, we can never be absolutely certain. So, this answer or this conclusion that we are going to make is called a conjecture or a hypothesis, and it's just an educated guess that can be tested. So we could go to the beach on Sunday, we could go to the beach on Tuesday, and we could see what the traffic was like to see if her hypothesis, whoever went to the beach, if they were right or not. So conjecture, hypothesis. A strong inductive argument does not guarantee the truth of the conclusion, but rather provides strong support for the conclusion. If there is just one case that it might not be true, it's going to be called a counterexample. So it's not, whatever inductive reasoning solution or statement you come up with does not necessarily mean that it's right. You just think it's right because of all the facts that you have at your fingertips. So, no, it's not 100% positive. And then, if we want to prove that it's wrong, what we need is a counterexample. And a counterexample is an example, just one. You don't need all of them, just one example that the conjecture is false. All right, so let's go through a couple examples here. In the book at the bottom of page 3 is example 1, and it says the 10 symbols that we use to write numbers, namely 0 through 9, are called digits. In each example shown below, the sum of 2-digit numbers is a 3-digit number. So the sum of 2, sum is addition. So whatever we add together, 47 plus 73, we're saying that it's always going to be a 3-digit answer. And so if it's a 3-digit answer, when we add those two up, you get 120. If we said 56 and 46, we add those two up, we get 102. So we're saying every time you add two 2-digit numbers, you will get a 3-digit answer. Well, if I wanted to find a counter example to that, I need to find two numbers that when added together, it's not 3 digits. So what if I said 56 and 43? That would be 99, and that's only 2 digits, not 3 digits. So this would be a counter example to this inductive reasoning conclusion. Okay? All right, so after example 1, you're going to try checkpoint 1. In the book, it's in the middle of page 4. If you want to pause your video and then come back, you can see if your answer is what you were looking for. So hopefully you have an answer. This one says the product. So if we say the product of two 2-digit numbers is a 3-digit number, and that's going to be, we want to make a counterexample to make that false, we could 10 times 10, that's 100. So that is not, because it works, that's not going to be a counterexample. But we could do 50 times 50 and get 2,500, and that has 1, 2, 3, 4 digits, not 3, and so that would be a counterexample. That we have there. All right, now you may have had another one. It does not have to be the same numbers. It can be two different numbers. 50 times 51 would be 2550. So again, that still works. It just doesn't have to be the same. All right, let's go on to example 2. This one is at the bottom of page 4. It says identify a pattern in each list of numbers, then use the pattern to find the next number. So if you want to pause the video here, these are examples, but I'm going to go through them real quick, and then you can try some of the next ones, or you can pause and try these and then come back and see if you got them right. So the first one is going to be adding 9 every time to get the next term. And so 39 plus 9 is going to be 48. The next one, 3, 12, 48, and so on. Here we're going to get 3,072 because we are multiplying by 4 every time. So 3 times 4 is 12, 12 times 4 is 48, 48 times 4 is 192, and so on. All right, this one's a little bit different. It doesn't look like we are adding the same thing or multiplying by the same thing. So we look and we go, okay, well, this is adding 1, and now we're adding 2, and then we're adding 3, and then we're adding 4, and nothing stops and repeats. So this adding of one more number would say I would add 6, and 18 plus 6 is going to be 24 for our answer there. And then this last one, here we can add 3, but 6 to 18, we don't add 3, we don't add 4, we actually would add 12, which is a little bit weird. So we could also say 3 times 2 is 6. All right, well, I could either add 12 or I could multiply by 3 to get the 18. So then we go to the next term to check on it. And how do I go from 18 to 36? Well, I don't add 3, don't add 12. Not really sure what I add there, so it doesn't really give me a good pattern, but I do know 18 times 2 is 36. And then I look like, oh, okay, this is alternating back and forth. So 36 times 3 makes 108. 108 times 2 makes 216. So 216 times 3 is going to be 648. And then I'd multiply by 2 and 3 again if I wanted to keep going in my pattern. All right. So if you want to go to the next one, check point 2, pause your video, try those out, and then come back and get the answers. So in this one, our answer is going to be 33 because we add 6 every time. In B, the answer is 1,250, and we're multiplying by 5 every time. In C, a little bit tougher as they go on here, this one is 3,456, and the reason is a repeater. We're going to multiply by 2, then multiply by 3, then multiply by 4, and then repeat. And then repeat that. So all that goes with what we're doing here in this list. And then D, the answer is 7. You're going to add 8, subtract 14, and then repeat. So that all goes with that last one. So hopefully you got those correct and you understand those repeaters. Example 3 is not so much adding or subtracting or something like that. This first one is actually called the Fibonacci sequence. And when you look at it, you're going to add the 2 numbers previous to get the next term. So there's nothing here, so technically that's a 0, and 0 plus 1 makes 1. 1 plus 1 makes 2. 1 plus 2 makes 3. 2 plus 3 makes 5. 5 and 8 make 13, and so on. So 13 and 21 make 34. So this would be a 34 in there. All right, this next one, B, this is the hardest one that you do, and you probably won't even do one like this in your homework that's this difficult. You can pause the video anytime you want, of course. If you want to check this out before I do it, go ahead and pause. On this one, if you look at the last digit it goes up by 1 every time. So this last digit will be a 9. If you go through here and you look at 2 plus 3, it makes the first part of the next term. 5 plus 4 adds up to 9. 9 plus 5 adds up to 14. 1 plus 4 plus 6 adds up to 11. So that's how we get that next term. So on here, we would do 9 plus 8 makes 17. So the whole next number is 179. That's a good, tough one. But I always have somebody that usually gets that one right. All right, if you want to pause here, you can try checkpoint 3 and then come back and get the answers. All right, so this one is going to be 76 because we add the 2 previous terms. So 1 plus 3 makes 4 and so on. And this one is going to be 257 because you're going to add double the previous amount. So here we would add 1 and then double the 1 and you add 2 and then double the 2 and you add 4 and then you add 8 and so forth. There is actually another one on some of these, and this one has another one. You could take the first number 2 and multiply it by 2 and subtract 1, all in the same thing. So 2 times 2 minus 1 gives you 4. Then you would say 4 times 2 is, I'm so sorry, it doesn't give you 4, it gives you 3. Let me get back to 3. And then you would do 2 times 3 is 6, minus 1 is 5. See how it matches? And then you do 5 times 2 is 10, minus 1 is 9. 9 times 2 is 18, minus 1 is 17. So these two are 2 different ways to describe what you're doing every time. All right. Well, it's not always numbers. Sometimes it's shapes or sometimes it's other things. So this one in the book on page 4 in the middle of on page 7, example 4 in the middle of the page, says identify the next pattern. So this one goes circle, square, circle, square. So the next one would be a circle. And it already has that, you would have the X in there automatically. And then it has those dots. So you got to figure out what do those dots do. Well, here's 1 dot. Now here's 1 dot. Then here's 1 dot. And so on. So they're rotating counterclockwise. So really it's going to look just like the first one did with 1 dot here and 2 dots here and 3 dots in that section of the circle. Okay. All right. Again, if you want to pause and try checkpoint 4, come back. This is what it looks like. Alternates shapes again, triangle to square, and then 1 leg, 2 legs, 3 legs, 1 leg, 2 legs, 3 legs. Okay. Here's just another real life one because it's not always numbers or shapes. Sometimes we get this. So a tourist who visits Key West met a number of people from the Keys who were relaxed and laid back. The tourist concluded that all people living in Key West were relaxed and laid back. So what reasoning is this? Hey, okay, so I met a guy who was relaxed and laid back. I met another guy who was relaxed and laid back. I met another lady who was relaxed and laid back. So there's my pattern, meeting people over and over and over. And so what is my conclusion? That all people who live there are going to be relaxed and laid back. That's inductive reasoning. The conclusion is called the conjecture, hypothesis. It's an educated guess, but you need to call it a conjecture or a hypothesis. Now, is it always true? No, because I haven't met everybody who lives in Key West. So there's probably somebody out there who is not relaxed and laid back. And when I find them, they would be called a counterexample. Here's a couple more that in class we skipped. So if you want to check those out, you can. And then the next part of this lesson is deductive reasoning. So we've gone from inductive now to deductive reasoning. And you're really going to flip-flop the things that you're talking about. We went from specific examples and made a general conclusion. Well, now we're going from specific conclusion based upon general examples. This can be proved that some conjectures are true, and if it is proved, it's called a theorem. We talked about in class the Pythagorean theorem, a squared plus b squared equals c squared, because it's always true for a right triangle that the two sides added together squared and added together will be the hypotenuse squared. Here's another example. The game Scrabble is that word game that you play and you try to make words, and you get points for however big they are and the letters that you use. Okay, so one player to another in Scrabble game says, you have to remove those 5 letters. You can't use the word Texas. Well, the reasoning behind that is because all, see how big and general that word is? All proper names are prohibited in Scrabble. Texas is a proper name, therefore, specifically, you can't use the word Texas in Scrabble. Okay? You are in Miss Pigot's, we'll say first or second or whatever class you want to be in. We'll say second period class. All right. Now, Miss Pigott only teaches applied math concepts. So you are in my second period class, so therefore you specifically must be taking applied math concepts. And the thing is, in class, of course, everybody's taking it, but somebody could ask you in the hallway, who's your math teacher? And you say, Miss Pigott. Well, because that's the only thing I teach, they could conclude specifically that you are the only one, or that you, are taking applied math concepts. It is required that high school students take 4 years of math. Holly is a high school student. Therefore, Holly has to take 4 years of math. All right. The cross-country team runs every day after school. Anna is on the cross-country team, so Anna runs every day after school. Okay, so we've gone from a more broad and general statement and narrowed it down to someone or something specific. Okay, so now we've talked about 2 different things, inductive and deductive reasoning. And this is your assignment for the class. Page 9 and 10, you're going to do numbers 1 through 41 odd and 57 through 60, all of those. And then I also want you to take a few minutes and think about how can you come up with your own inductive statement and deductive statement. And we'll talk about those in class when we get a chance. And